Thank you very much for the organizers for inviting me and organizing such a nice conference. So I'll talk about maybe two related works. One of them is mainly done with Zijian, who was a visiting student in Berkeley for about 9 months, and Riwa was a postdoc, and a related work with Vlad and Zach. Zach is here. He's a postdoc in Caltech now and was a graduate student in Berkeley until recently. And I'd also like to thank earlier work with Imu's here and Ashwin and Riwa also involved in that work. Okay, so in this audience, I guess I don't need to tell you that there have been recent experiments that were pretty exciting, showing various ways to create topological order and quantum topological codes in the lab in various different platforms. In all of these systems, the system is subject to noise, so these protocols actually prepare topological mixed, or they prepare mixed states, and to what extent they're topological is kind of a question. And this led people recently to think about more seriously about what happens to a topological state, topologically ordered state, when it's subject to noise and decoherence. So this is like a schematic illustration of this. Say you encode information in a topologically ordered state in the ground state subspace, but then you subject it to some finite depth quantum channel. This is a mathematical description of this channel using local Krauss operators. And it was basically understood that there is, in general, an intrinsic transition in the topological ordered state at a critical decoherence strength, or namely after some finite depth channel that depends on the depth of the channel. And this is closely related to an error threshold. Namely, for example, in the Tori code, it's exactly that. You start from the pure state at p equals 0 error probability. At some critical error probability, you lose the quantum memory. Then there is a trivial phase, and it's directly related to the error threshold of the optimal decoder in the Tori code. But because it's intrinsic to a topologically, it's an intrinsic transition in the topological order, it can be generalized to many other states that are not necessarily stabilizer states. But this transition can only be detected by information quantities. It's inherently an information transition. An example is the coherent information between a reference qubit that was initially entangled with your code. This is the coherent information. That's an example of a quantity that can diagnose this transition. So a natural question is, well, a lot of work was done on kind of demonstrating this in the Tori code and related models, but we know about naturally occurring topological states that are more generic, I would say, and are not in this stabilizer paradigm. And one can ask the question, what is their fate under decoherence, and what are their error correcting and error encoding properties? And kind of a very natural set of topological states to look at are fractional quantum Hall states. So this is kind of the famous phase diagram, if you want, of fractional quantum Hall states as a function of magnetic field. You see there Hall plateaus at fractional fillings, and we know that they correspond to different topologically ordered states. Each of these states has a topological degeneracy on a torus or other non-trivial topology manifolds. They have anion excitations, either abelian or non-abelian, depending on which quantum Hall state we're looking at. They show charge fractionalization, edge states. And they've been known for a very long time. As you see, that this was adapted from a pretty old paper, and actually reasonably well understood for a long time. So it's natural to ask the question and seriously treat the question of what happens when they're subject to noise or decoherence. What is their capacity for encoding quantum information in this case, and so on. So why look at fractional quantum Hall states in particular? Apart from the fact that they're so neat and well-known and famous and have been around since many of you have not been born. Well, apart from that, first of all, from the point of view of quantum information, well, as I said, we can encode quantum information, at least in principle, in fractional quantum Hall states into their degenerate ground states. That's one thing. Second thing is that we can also encode information into the fusion space of non-abelian anyons in fractional quantum Hall states. That's also well known, and people actually, the whole idea behind Microsoft's enterprise and quantum computers is to use this fusion space as a way to do protected quantum computation. And one can ask, how resilient is the information encoded in the ground state and in the fusion space of non-abelian anyons? So this is from the point of view of quantum computation. From the point of view of many-body physics, first of all, they give us another paradigm of tractable systems outside of the commuting projector paradigm to understand general encoding and error correcting properties. And second, people have recently looked at kind of a generalization of topological order to mixed states, and these states bring new elements that are interesting and kind of non-trivial. First of all, they're chiral topologically ordered states. They have U1, they respect the U1 global symmetry because of charge conservation. And in addition, decoherence, so because of these new elements, decoherence can lead to new kinds of mixed state phases. So in this talk, I'll mainly talk about the simplest fractional quantum Hall state, which is the Laughlin state. But actually, I have more to say about more read states that are non-abelian states. I probably won't get to it, except maybe flashing some results. But Riwa will be here in the workshop later on, I think in October, and I hope he gets a chance to talk about it. Maybe it's even more exciting for some people, but it's more technical, and I want to get the ideas through for the simplest type of states. So I'll start from the Laughlin states, and a brief review of Laughlin states. So for example, these occur at a filling factor of 1/3. Filling factor of 1/3. This is the famous Laughlin wave function. This is the many-body wave function that kind of describes the universal, essentially all the universal aspects of this state that Laughlin kind of dreamed about in 1983. It describes a gap state in the lowest Landau level at this filling factor with an odd denominator for electrons. It would be even denominators if the particles were bosons. The ground state has a degeneracy of M on the torus, and this is where you can encode quantum information. And it has quasi-electron and quasi-particle that are excitations that are anyons with fractional statistics. The phase of braiding them around each other is this theta, and the fractional charge. Okay, so we'll need physical models to describe what kind of an error model or a noise model to which we subject our fractional quantum Hall state, and we'll want to ask what happens to the quantum memory that we encode in it under these noise models. So this one simple noise model would be kind of, I call it high frequency noise or high frequency dephasing. It's noise that couples to the microscopic electron density and has kind of a very broad bandwidth, doesn't care about the Landau level gap at all. So this is basically the Lindblad equation that describes this dephasing in terms of density, and it's kind of easy to solve, especially if I write the density matrix as a state in the double Hilbert space. The evolution is basically imaginary time evolution with this simple operator in the density representation. So because it's so simple in the density representation, you can see immediately what it does to a density matrix in this representation. Basically, it keeps the original density matrix, which was just the Laughlin state, in the density representation, but any off-diagonal element is being suppressed exponentially in time. Sorry, this mu is gamma times t. So you basically suppress off-diagonal elements in density exponentially in time. That's what I think you intuitively expect dephasing in the density channel to do. The second physical noise model, which I call low frequency noise. So what happens if you subject your sample to kind of noise below the Landau level gap, maybe even below the average quasi-particle gap. So I'll talk about a phenomenological noise model in which basically you create pairs of quasi-particles and quasi-holes or hop them around between defect sites where they have like a preference to live. For example, if the gap is smaller in these defect sites. So this is another kind of physical noise. Another kind of physical noise you can imagine is particle loss. For example, if electrons are hop on and off from your sample. I'm not going to talk about this. I'm going to talk about the first two, which are kind of simpler and also respect the U1 symmetry that we have in this state, and that's part of what we're interested in. So let's start from the density dephasing, and I'm going to use the most elementary level to treat this in Laughlin state, which is to use the famous plasma analogy. So the plasma analogy comes from, maybe I can take a step back and remind you of the Laughlin wave function. If you look at the Laughlin wave function, absolute value squared for, it looks like a Boltzmann weight for a plasma, because you can write this polynomial with e to the minus log interactions between I and j. So if you take the norm, it's basically the partition function of a plasma of charges square root of 2m with a neutralizing background. So the partition function, the normalization of the wave function maps to a nice statistical mechanics problem. And this is actually how Laughlin solved a lot of the correlation functions in this state. It's well known now that it describes a plasma in a screening phase as long as you're with m smaller than about 70. So you're safe that you're in a screening phase of the plasma, and as long as you're in the screening phase, this is describing the topological state. Beyond m equals 70, this state doesn't describe a topological state anymore. But we are in the screening phase for reasonable m. So what happens when, instead of calculating the norm of the wave function, which is in some sense like trace of the unnormalized density matrix, we want to calculate trace of rho squared, which is the purity. It's the first nonlinear observable, if you want. And as I mentioned, phase transitions are for finite depth decoherence channels are going to appear only in nonlinear observables like that. In particular, the coherent information has a version that's Rayleigh 2 that is essentially composed of these these purities. So if we are going to see a phase transition, we better see it in this simplest quantity. So the nice thing about the Rayleigh, the purity, is that unlike the trace of rho, which includes only diagonal elements, of course, the trace of rho squared, if you put in a it has to include also off-diagonal elements. You have to sum over off-diagonal elements. So it will give you some information about the what happens during dephasing. Indeed, what happens is because you have both the right and the left of the density matrix, they correspond to, instead of what you get is an effective model for two plasmas, one representing the left side of the density, the ket side of the density matrix, and the other the bra side of the density matrix. And these two plasmas interact with each other via the dephasing, the dephasing strength. So what the dephasing wants to do is favor matrix elements, diagonal matrix elements, and suppress off-diagonal matrix elements. So it's a very strong attractive interaction between the plasma on the left and the plasma on the right that suppresses cases where the plasmas are misaligned. This is an off-diagonal element, right? So we have two plasmas and an attractive, short-range attractive interaction between them. So let's see what happens. Simple cases are mu equals 0, no decoherence, in which case the two plasmas are completely independent of each other. Of course, this is the pure state. The density matrix description is just redundant. It just describes two independent plasmas, each one of them in the Laughlin state. We call this the fully screening phase because each one of them is in the screening phase, so you screen particles both in the up and the down, or maybe in a different basis, both the center of mass particle and the relative charge is screened. On the other hand, when we go to infinite dephasing, then the interaction between the two sides, you basically are left only with diagonal elements in the density matrix, which means the particles in the two plasmas have to bind in tightly bound pairs, in which case these tightly bound pairs still form a plasma of these pairs. They still screen, but they only screen in the symmetric channel. They don't screen in the anti-symmetric channel of the charge. So we call this partially screening phase. And the question is what is the nature of the phase transition, if there is a phase transition between these two limits. Yeah. Oh, it's attractive because we have this, I mean, first of all, we know it exactly. In the density representation, it's just n1 minus n2 squared, right? So it's basically attractive interaction. It basically gives a smaller weight if n1 and n2, if the densities on the two plasmas are different at a given site.
But meaning that is that a property of the channel that you're studying?
Yeah, it's a property of the channel that the dephasing channel. The dephasing channel is, it can be written exactly as this kind of attractive interaction. That's right. And it's because it couples to density. It will always be in some sense attractive because it always will suppress off-diagonal elements in the basis that the jump operators are written in. Here it's very nice to study in this plasma analogy because plasma analogy is based on charge. So now you go to the infinite attractive interaction, you have this, and how to study this? Well, the way to study this is understand, so what happens is just like you do in other kind of bound plasmas, you want to ask what is the fugacity for unbinding a pair and asking when it will proliferate. And the fugacity for unbinding a pair, basically the energy of unbinding a pair is controlled by this fugacity e to the minus mu. This would be the, unbinding a pair, plus it would be an extra long-range interaction because of the Coulomb interaction between the charge that's left behind and the extra charge you put here that gives you an energetic cost of m times log of the distance. And there is also an entropic gain from having such pairs that goes like log of the L squared times R squared, and if you want, we're interested in the longest possible pairs that are order L, and that gives you an entropic gain of 4 log L. And if you balance the energy cost and the entropic gain, you immediately see that you expect a transition, which is essentially Kosterlitz-Thouless-like, exactly at m equals 4 for this Renyi-2 thing. And you can formalize this using kind of KT like RG and see that there are these two phases. And I should note that the physical route you go in this dephasing is you always go vertically, right? Because you stay in the same. I should note that what plays the role of the stiffness or the temperature is exactly the filling factor 1 over m, or m is the stiffness and inverse stiffness is m, because that's what appears, in front of the Coulomb interaction. So there is a one-to-one correspondence with Kosterlitz-Thouless physics, but the bare and the level of the Chern-Simons theory just plays the role of the bare stiffness. And so as a function of increasing dephasing, you stay at the same m, but you go down like this. And the question is whether you pass this separatrix. Once you pass the separatrix, you go down to this partially screening phase, which is a critical phase of the Kosterlitz-Thouless, in the Kosterlitz-Thouless transition, and presumably lose the encoding properties. We'll check that. That is the conjecture for now. And if you, but before that, your pairs are not unbound, and ultimately you go back to the screening phase, and presumably your information remains. That needs to be checked, but presumably. An interesting point here is that it looks like if our m is below 4, or the filling factor is larger than 1/4, then no matter what strength of decoherence we put in, as long as it's not infinite, we'll go back to the screening phase. So the system, it's already a pretty strange prediction that these states are going to be absolutely stable no matter how strong the decoherence. Well, here we'll have a transition, sort of like in the toric code. Okay, I said we need to check whether indeed the quantum memory is lost or not. The way to check that is an intrinsic measure of the quantum memory is the coherent information. So we encode by entangling our code space with some external qubit, or for m equals 3, but an external state. And we want to calculate the density matrix rho RQ so that we can compute the coherent information, the difference between these two entropies, S of Q and S of RQ. And this is known as the amount of information that you can recover locally by acting only on Q. And it's a quantity that goes between minus log m, when you lose all information, classical or quantum, and log m, which would imply that you have the full information recoverable, all the quantum information recoverable. And when I see the coherent information hit 0, it means that you cannot recover any quantum information. Oops. Sorry. What happened here? Yeah. Well, to diagnose the quantum memory, we're going to do, we're going to use the Renyi version of this quantity, actually. Okay, so the problem here, I can't use the plasma analogy. The reason I can't use the plasma analogy is, first of all, because my computer is not responding, but second is because in the plasma, in order to entangle my code space with an external qubit, I need to be able to write the wave function in the Laughlin wave function on a torus. And on a torus, I have different sectors. I need to be able to write all of them. In the plasma analogy, it's very, very complicated. Or to write the Laughlin state like that is very complicated. It's much easier to use a field theoretic approach for that. And one way there are actually two ways we can develop the field theory approach. The way I want to present it now is using well-known bulk boundary correspondence. Basically, we can write the Laughlin state using the correlators of some edge CFT, and it's well known that for the case of Laughlin states, the edge CFT is a single chiral boson. It's called U1 level M CFT. The electrons operators in this CFT are e to the I n phi, while the primary fields are e to the I n phi with I going from 0 to m minus 1, and they create the anyons of this theory. And the Laughlin wave function is exactly given by inserting electrons in positions, in the positions I, times a term that gives you the neutralizing background charge to these electrons. So if you insert that and calculate the correlation function of this object, the expectation value of this object, so it's an endpoint correlation function in the CFT, which is what I do here, you get exactly the Laughlin wave function. Okay, so Laughlin wave function has this nice CFT description. What is nice about it, it gives us, now if we rewrite we can, just like we can write the wave function, we can also write the trace of the density matrix squared in this way. And in the wave function, we had each wave function corresponded to a single chiral boson CFT. Now, if I look at the density matrix corresponds to two such chiral bosons, chiral and antichiral, one coming from the left, one coming from the ket and one from the bra, which here is 1 and 2. And then there is a second density matrix because we have rho times rho, and I call that right and left. And from there, we have another two sets of chiral bosons. So altogether, this is given by basically two non-chiral bosons, chiral and antichiral mode, chiral and antichiral modes, CFTs. So it's like an edge state problem. And but they're coupled. So this is the interaction between them. And the interaction between them can be written down exactly. It comes both from the fact that we need to glue the right and the left to each other in this trace because they're multiplying each other, and because that is the interaction between left and right. And there is also an interaction between the 1 and 2 due to the decoherence. So that comes from the density-density interaction here. So we can write down the interaction between them exactly. And if you write it in terms of the fields phi plus and phi minus, which correspond to these two bosonic theories, one of them, so phi plus, just to be, phi plus is a field conjugate to n1 plus n2 to the center of mass charge, and phi minus is a field that's conjugate to n1 minus n2. It's exactly like the relative charge. If you write it like that, this interaction looks like a delta function of phi plus. So phi plus is always completely pinned, which means that the center of mass component is always going to be in a screening phase of the plasma. This is not surprising. This we know also intuitively that, when even at infinite decoherence, the center of mass component stays exactly as it was. But the interesting component is, because of this chemical potential, is because of this Fugasti term, is the relative, the conjugate to relative charge. Yeah.
Phi plus is phi 1 and phi 2 from the two copies, both on the left or right?
No. Yeah, phi 1 and phi 2 are from the two copies. Phi 1 and phi 2 are from the two copies. Yeah. Yeah, and phi 1 is basically the chiral plus the anti-chiral component of 1 and phi 2 the same for 2. Yes, sorry, these are non-chiral fields. So basically what we have is an effective theory. One theory is always gapped, so the phi plus theory we can throw away for now because it's always gapped, not changing at all. The only thing that's changing is the relative component, which is conjugate to the relative charge. This is what we expected will have some, yeah. Yeah. Phi 1 and phi 2 correspond to the same density matrix left and, and the left and right part, sorry, there are two, so phi 1 and phi 2 are not from the same density matrix. Phi 1 is from the ket, phi 2 from the bra. And phi 1 has both density matrices in it because it has the left and the right. Yeah, right. So all the action is occurring as we expect in the relative charge channel, which is we write the field theory in terms of the conjugate to the relative charge, and this is just a Sine-Gordon theory. It has this phase so this is just another way to express the same KT transition that we saw in terms of a Sine-Gordon model. So nothing new yet. The nice thing is that we can write the different ground states using this, and the different ground. So by writing the different ground states, we can write down the Rayleigh 2 coherent information, and it turns out to be log of sum of ratios between two partition functions, or if you want to, you can think about it as a sum over e to the minus differences in free energy, where these partition functions correspond to different twisted boundary conditions on the field phi. This is z tilde, and zn on the is different twisted boundary conditions of the dual field theta. It's a dual field to phi. So what do you get? Well, in the fully decoherent phase, e to the minus mu is 0, and you have just this non-interacting theory. In this non-interacting theory, phi and theta it's a self-dual theory, and because of this self-duality, you get that zn tilde and zn must be the same, which means that this is 1, and the coherent information is exactly 0. So in the fully decoherent state, we get that there is no coherent information, not too surprising. The other thing that we get that's kind of a good sanity check is that in the encoding phase, the coherent information is exactly log m, and this is because the cosine is relevant. If you stick the twisted boundary condition of phi into the cosine here, you will pay a price L, except for the case n equals 0. So only the case n equals 0 is contributing, and you get log m. So this is again, the encoding phase for mu less than 0 is fully encoding indeed. The non-trivial thing, and kind of surprising, is that the decoherent phase, where mu is greater than mu critical, but it's not yet, fully decoherent, you can treat the cosine perturbatively, and you get that the coherent information is somewhere between log m and 0. So what happens is that as you tune the decoherence, well, first of all, if you're above the critical filling factor, it doesn't matter how much you tune, you have the full coherent information. In the case where mu is less than the critical filling, you have a jump at mu c, and the critical phase corresponds to a phase with some partial coherent information, non-universal. Okay, so let me skip to the second part. So let me skip to the second part. I just want to note that all this was for 2 replicas, but we can actually make some progress at for the von Neumann quantities, and we find that basically there is the same physics, except we don't know the critical filling factor exactly. We can bound it between 1/8 and 1/4 for the actual von Neumann quantities. I want to just briefly talk about Laughlin state subject to low frequency noise below the gap. And there we have a phenomenological error model. This is done with Zach and Vlad. The phenomenological error model, you can imagine that, well, you have very, very low frequency noise, and it essentially creates pairs of quasi-particle and quasi-holes only in defect sites where it's more favorable for them to be created, and hops them around. So you can imagine this is basically a very similar model to decoherence in the toric code, Pauli noise in the toric code, where the noise basically creates pairs and takes them around, right? So you can think of these as the error strings, and the syndromes are the divergencies of these error strings. Looks like electric field. And you can now use the information about measuring charge in the decoding, and one can write a statistical mechanics model that, again, very similar and closely related to the one you write down for the toric code for the optimal decoder. Basically, you get a loop model like that that's anchored on the syndromes. The syndromes basically give you quench disorder. It's almost the same, except these are directed loops, and directed loops is because the anions always come in plus and minus pairs, so you know that the error strings had to go from one side to the other. And this is this directed loop model is exactly dual to a disordered XY model at some inverse temperature beta. And in the optimal decoder, we have the Nishimori condition where the probability for error and this beta are the same. And here is the phase diagram we get from Monte Carlo calculations of this model. And well, an important quantity here is the Helisti modulus, which is the variance of the winding numbers of these loops. You can imagine that if the variance, if the winding number squared average becomes large, it means that we have fluctuating winding number. It means that we can't really ascertain the homology class of the error, in which case we're not going to be able to recover. So this is closely related. Actually, we really need to look at just the first one in order to know whether it's recoverable or not, but the universal features correspond to, at least in this transition, are encoded in the Helisti modulus. And what we find, first of all, what we know analytically is that here there has to be a clean KT transition. This is no disorder point. It's a clean KT transition. For weak disorder, we can understand what's going on here, and we understand that there is a continuously varying critical line with continuously varying stiffness jump. Beta is like the temperature of the loop model, and it's the inverse temperature of the dual XY model. So that's why this phase is really the critical phase of the XY model, and this is the disordered phase of the XY model. Now, the Nishimori transition, we see that it actually follows really beautiful KT scaling. So this looks like the continuous KT transition here goes all the way to the Nishimori point, and then then something weird happens. This is quantum memory phase, no quantum memory. We also understand what happens in this point. Well, we can compute at least. This is sort of like the analog of minimal weight perfect matching, which gives us not the optimal, but an efficient decoder here. And it corresponds to a problem called minimal cost flow decoding, and we can do it here. As you see, it's not optimal, but it's pretty good. That's the error rate. also has some critical exponent. It's nice. The surprising thing is that we find another phase here, which is no memory. It looks like a glass. In this case, both the variance of both W squared average and W average squared are both non-zero and cancel each other so that the helicity modulus is zero. Or in the dual XY model, there is no stiffness. So kind of nice stat-mech model. You can also do fault-tolerant decoding for faulty measurements in 3 dimensions. We get a threshold for this. It's also an XY disordered Nishimori XY transition. So this is the summary. I showed you 2 types of decoherence you can have on Laughlin states. A surprising result is that for high bandwidth dephasing noise, Laughlin states are absolutely stable for above some filling factors UC, and in particular, 1/3 Laughlin state is in this ultra stable mode. And this is just for this kind of dephasing. There is an interesting, in the low frequency noise for phenomenological error model, we have efficient decoder and interesting statistical mechanics model that describes the optimal decoder. And just to flash the Moore-Reed state, so probably maybe just advertise when either talk to me about it or hopefully Riwa can give a talk about this. You can ask, in the Moore-Reed state, you have non-abelian anyons. You can ask about what happens to the information encoded in the fusion channel. And there are also surprises about this, and maybe I'll just tell you the result. The result in the end is that it was surprising to us that actually the Laughlin component of the Moore-Reed state basically has the same physics. That's not surprising. It has a partially screening phase and a screening phase. But the Ising CFT component is ultra stable always. So it always, no matter how strong the decoherence is and no matter what's the filling factor, it's always ultra stable. So yeah, that's it.
Yeah, thanks, Ehud, for a very nice talk. First question is here, check it.
Yeah, right. So can we go back to the first field theory like this? So there should be 2 U1 symmetries. I did wonder what are the 2 U1 symmetries in your field theory?
It's like U1 left and U1
right.
right.
Yeah, so your field theory should have 2 U1s, right?
Yeah, and actually you have 2. Well, there are actually 4 U1s because there is also magnetic and electric U1. But just electric U1 symmetries, there are 2 U1 symmetries. In the field theory, there are 2, right? The field theory has...
You have phi minus and...
It has phi 1 and phi 2. They're both 2 field theories, right? So
yeah.
Right. So at least in the...
Okay, you have 4 U1, but then the cosine term and the delta function remove 2, so you have 2 U1s left. I think that's what's going on. Can I ask one more thing? Okay, yeah. So in the end, for the Moore-Reed state, right? So right. Suppose I condense the abelian anion, for example, then the Ising anion will also be confined. I think because
so this what I showed here is actually a different kind of noise. It's not incoherent noise in terms of anyons. It's a noise. It's incoherent noise in terms of the electron density. And it's very complicated in terms of anyons. And that's what makes it actually simple to solve in this case. Yeah.
We don't have any more talks after this, so we can just go on with questions for 2 hours. No, but thank you for the talk. It was great. So at a physical level, right, of course we can try moving anyons physically just by, like, I don't know, taking some STM thing and hooking on them.
Yeah.
But like in reality, they could interact, right? Could we induce some sort of attractive interaction? Is there like do you think there's some really like physics-based way to?
You mean interactions within the same plasma, basically?
Yes, yes. What I'm asking is like, is there like a physics-based way to decode, right?
Oh, yeah, I haven't thought of that. That's like make them kind of attract with a Coulomb interaction and kind of kill each other.
In the code, people have tried.
I know, right? That would be really interesting. I think because the Coulomb interaction is 1 over r and not log, right? The real Coulomb interaction, if it was log, probably it would help, right? But so you could maybe do it approximately by screening or something.
But also in the Torah code, the way people try to induce it is by coupling it to some like bosonic bath, right? And then you can kind of control that. So maybe here there's some way to control it as well.
I think by maybe metal leads or something, you can create for some range of logarithmic interactions between charges. Maybe that would kill the quantum Hall states. I don't know. I mean, things are fragile, but yeah, but that's a good idea. You could imagine trying to utilize the Coulomb interaction somehow to do the kind of to make them more stable.
Thank you.
Hi, yeah, just a quick question. For this decoding, I guess for the other kind of noise, like if you had like the 1/3 state or something, where you have sort of Z3 fusion, are you guaranteed because of the charges that the anyons carry that you still have this matching problem rather than like a clustering problem for your decoder, or?
It's a very good question. The problem we solved is a problem that wants to return us to the same ground state. But in principle, you can say you want to return to like a neutral state under the topological order. So you don't need to match anyons. So that's a different problem that would correspond to a different decoder. If you don't mind kind of having loose charges integer charges hanging around, then you could do some kind of clustering problem that would be different. I agree. Already this decoder is much more efficient than, say, the Torah code because you have information about charge. You might be able to do even better by some kind of clustering method like that. And then you say, okay, I can clean the charges after.
I guess even if I am still restricting to the charge neutral case, I can still consider like a scenario where I have like 6 anyons, right? Where the overall thing is charge neutral, but the matching
you mean charge
is...
neutral or charge or just topological charge neutral?
Or I mean charge neutral, like a hole that's split into 3 and then
in principle.
But you're saying you can still just
our noise model, I think our matching is kind of taking care of all of this. This it is taking care of. And in fact, the noise model doesn't allow 3 to be created. It only has 2. So our noise model has just, we can in principle have a different noise model that allows like creation of 3 quasi-particles that have 0 charge. But we don't have that in our noise model. But I think it will give the same universal behavior in the end, but this kind of model. But yeah, what I was answering is there is a different issue that in principle you could decode correctly without going back to the same state because you could leave a charge excitation under the global U1 around. And that we haven't taken into account.
I guess those are transparent to the braiding.
Yeah.
Okay, experimentalist question. Right, so you started out with 3 sources of decoherence, and there's a lot of work to prove rigorously about the robustness, but how much does it tell me about the robustness that people see fractional quantum Hall states in transport with electrons tunneling on and off? Like,
Yeah. Well, first of all, electrons tunneling on and off is a kind of noise I didn't even consider.
I guess I'm just sort of saying, like, the real experiment has electrons tunneling on and off, and it has all sorts of noise processes, and yet you see fractional quantum Hall signatures.
Right.
Like,
yeah, so there are different, it's a very good question. So I want to set some things straight. So first of all, in fraction and quantum Hall states, systems are usually at finite temperature even, which is far worse than the kind of decoherence I'm talking about, which is a finite quantum channel. Finite temperature means like an infinite depth channel, and we know it's not robust to that. So you can ask from the start, why do I see quantum Hall states and quantum Hall effect, although it's at finite temperature? And the reason is that if the temperature is below the gap, you can still see good signatures of the state, so the quantization would not be exact, but you'll see almost exact quantization. The topological order is not strictly speaking there, but at the finite size system, it's kind of morally, you can think of it as a so I think, and second, these physical signatures correspond to observable correlation functions. They don't tell you about whether information is encoded or not encoded in the system. This is much harder to observe whether it's still encoded or not. First of all, experimental systems are not on a torus. That's why it's actually interesting to talk about fusion channels of anyons, because it's hard to put fractional quantum Hall state on a torus, although there are geometries that make it kind of possible, I think.
One quick final question.
It's just a quick question. So I want to ask if the anion properties, whether they can be determined by things that are linear in the density matrix.
Why they can not be determined in terms of linear in the density matrix?
I mean, it seems like you need some information theoretic quantities to diagnose these transitions.
Yes, yeah.
But it seems that anion fusion rules can be measured by something linear.
Well, not whether you see the fusion rules or the information in the fusion channel is something different, I think. So first of all, any kind of linear observable is not going to have a phase transition at finite depth, because at finite depth you can purify the channel and then it's a finite depth unitary of your quantum Hall state plus a trivial ancilla state. So any kind of linear observables, I don't think can have a phase transition here. So I'm not sure how you would define exactly fusion channel if you have some kind of time-dependent state, but probably you can still ask about braiding and you can probably still ask questions about braiding and see if it's approximately there. It's a good question, but I think questions about whether the information encoded in the fusion channel is there or not is not going to, you cannot extract it from any linear observables. You'll need to somehow decode the information, and that decoding is nonlinear.
Thanks. Yeah, let's stop here and move all further questions to the coffee break, and let's thank Ehud one more time.